Good afternoon, students. In the previous lecture, we studied source-free RLC circuit. In this lecture, we study step response of series RLC circuit and parallel RLC circuit. That means the response of the circuit when we apply a voltage source. For example, a DC voltage source at t equals to 0. In this circuit, you have series RLC circuit, and at t is equal to 0, the switch is closed, means the supply voltage, the circuit is getting the supply voltage Vs. Now, applying KVL across the loop, the voltage across the inductor plus the voltage across the resistor plus the voltage across the capacitor is equal to Vs, the source voltage. LdI by dt plus R times I plus V is equal to Vs. But we know that the current I is CdV by dt. So we substitute this in this equation. So when we substitute here, this will become second derivative. Okay, it will become LC, second derivative of V by dt. And this will become R times C dV by dt plus V is equal to Vs. Then after rearranging, we get this equation. Second derivative of V plus R over L dV by dt plus V over LC is equal to Vs, the source voltage, over LC. If we see this equation, if the source voltage is equal to 0, then it will become source free. And with source free, we have this equation. It is similar to the source free RLC circuit, but the only difference is in the source free RLC circuit, the parameter was the current I in the circuit. But here, the parameter of interest is the voltage V across the capacitor. So that's the only difference. Otherwise, alpha and omega naught are the same. So we have the total solution of this is the combination of the transient response plus the steady state response. The transient response is the response without the source. That means Vs is equal to 0. And the steady state response is the response due to the source Vs. So the total solution is the transient response plus the steady state response, or we call it the forced response. And the transient response, we call it the natural response. Now, the transient response or the natural response is the same as it looks. It has the same form with that of the source-free RLC circuit. So I will have the overdamped case, the critically damped case, and the underdamped case. So we will make all independent source 0. That means if there is independent voltage source, we replace it by short circuit. Independent current source, we replace it by open circuit, and we'll find the transient response. Either it will be overdamped, critically damped, or underdamped. What about the steady state response? The steady state response is the response after the transient response has died out. So what will be the final value, for example, of the capacitor voltage? If we see this circuit, after the switch is closed and after a long time, then the capacitor will be open circuit, the inductor will be short circuit. So the final value of the capacitor voltage is the source voltage. So it's very easy. The steady state response is Vs. Therefore, the total solution is the steady state solution Vs plus, if it is overdamped, the transient part, and if it is critically damped, this one, the transient due to critically damped, and if it is underdamped, this one. So now what are the remaining parameters to be solved? A1 and A2. Where we get them? From the initial conditions. The initial voltage across the capacitor plus the derivative of the initial voltage across the capacitor dV by dt at 0, which is IC at 0 divided by C. Let's have this circuit. Okay, for this circuit, determine the voltage V of t and I of t for t greater than 0. Now, for t less than 0, the switch was closed. The switch was closed means the inductor and the capacitor are in a steady state. So the inductor is short circuit, the capacitor is open circuit. So we will have a 1 ohm and 1 ohm resistor in series, okay, with 24 volt source voltage. Of course, for t greater than 0, the left part of the circuit will be 1 ohm, 1 henry, and the capacitor. Now let's determine alpha. Alpha is R over 2L. So it is 1 ohm over 2 times L is 1 henry, 0.5 omega naught. We substitute L and C is 2. So we see alpha is less than omega naught. So what kind of solution we get? Underdamped. So the voltage across the capacitor with time V of t is Vs, the steady state value, plus e to the power of minus alpha t, a cos omega dt plus a2 sin omega dt. Omega d, where we find it? From square root of omega naught square minus alpha square, which is 1.936. Now, what is the steady state value of the capacitor voltage? Simply, it is the source voltage, because in a steady state, after t greater than 0, remember the right part of the circuit is disconnected. Then 1 ohm, 1 henry, and the capacitor are in series. Then the inductor is short, the capacitor is open. So the steady state value of the capacitor voltage is 24. Therefore, the solution is the steady state value plus the transient value, this one. So what is the remaining A1 and A2? Where we solve them from the initial condition. The initial condition for t less than 0, the capacitor is open circuit, but the inductor is short circuit. And we know the current through the inductor does not change abruptly. I at 0 minus equals I at 0 plus I at 0, which is equal to 24 volt over 2 ohm 12 ampere. And the voltage across the capacitor is the same as the voltage across this 1 ohm resistor. I at 0 times 1 ohm is equal to 12 volt. So if we substitute t equal to 0 here in this equation, a1 cosine 0 will become a1. This will become 0. So 24 plus a1 is equal to v at 0. So we get a1. So where we get a2? From the second initial condition, dv by dt of at 0. We know that I at t cdv by dt. So I at 0 means cdv by dt at 0. So the derivative of the voltage across the capacitor at 0 is I at 0 over c. I at 0 over 0.54 times I at 0, 48. So we have the second initial condition. Then we make the derivative of the complete solution. The derivative of the complete solution, remember, it's the product of two functions. So it will be the derivative of one of the functions times, for example, here the derivative of e raised to minus alpha t times this, and then the derivative of the second part times this. And by doing so and evaluate at t is equal to 0, we get this. Therefore, we have a1 this and a2 this, and finally the solution this. The current I at t, the I of t. What is the current of I of t for t greater than 0? It is c dv by dt. So we take the derivative of this. What is the derivative of this? The derivative of the first one is 0, since it is constant. And we make the rule of derivative for the product of two functions and simplify, and finally we get this. This is an exercise practice problem for t less than 0, the switch was in A, and then at t equal to 0, it is going from A to B, and we have a series RLC circuit, and we need to find the voltage V of t using the initial condition V at 0 and the derivative of V at 0. Okay, source-free parallel RLC circuit. Okay, for the parallel RLC circuit, again we make KCL. Okay, at t equal to 0, this switch is open. That means there is a source current IS for the resistor, the inductor, and the capacitor. So by taking this node, we have V over R plus I C dV by dt is equal to IS. C dV by dt is the current through the capacitor. V over R is the current through the resistor. But V is L di by dt. V means the voltage across the capacitor is the same as across the inductor, the same as across the resistor. And we substitute this value here, and after rearranging, we get this equation. Okay, this is second order equation, but the parameter is the current I. So if there is no source, if it is source free, IS is equal to 0, then it looks like the source free parallel RLC circuit equation. What is the difference? In the source free parallel RLC circuit equation, the parameter was V, not I. Okay, so otherwise alpha is the same. Alpha is 1 over 2 RC. Omega naught is square root of 1 over LC. So we have, again, for these two solutions, the transient response and the steady state response. And the transient response, it can be overdamped, critically damped, or underdamped like before. And the steady state response is the response of the current in the long time, okay, after the transient response has died out. For example, for this case, the IS, because the inductor will be short circuit, then this IS will flow through the inductor. At t is equal to infinity, the inductor current will be the same as the source current IS. It will be the source current IS. So we have the total solution, the complete solution, which is the steady state value plus the transient value for the overdamped case, and the steady state value plus the transient value for the critically damped case, and the steady state value plus the transient response for the underdamped case. Again, for this, we need two initial conditions. One, to solve for A1 and A2, the current I at 0 and the derivative of the current at 0. The derivative of the current I at 0 is VL at 0 divided by L. Then we solve A1 and A2 or B1 and B2. Let's have this example. In this example, find I of t and IR of t for t greater than 0. Okay, for t greater than 0 means this switch is closed, and for t less than 0, it was open. So for t less than 0, only the 4 ampere and the 20 Henry inductor, they are in series. Okay, and what will be the current I at 0? Of course, this will be short, and then I at 0 will be 4 ampere. This is for t less than 0. For t greater than 0, now if you see this, the voltage source, it is 30 times U minus T. U minus T means the unit step function, which is equal to 1 for t less than 0 and 0 for t greater than 0, which means for t greater than 0, there is no 30 volt. This will be short. For t less than 0, there is 30 volt. But for t greater than 0, there is no 30 volt, and this one will be short. So, for t less than 0, the capacitor acts like an open circuit, and the voltage across it is the same as the voltage across the 20 ohm resistor, which is connected in parallel with the capacitor. And by voltage division, V at 0 is 30 times 20 over 20 plus 20, which is 15 volt. Now for T greater than 0, we have the 20 ohm resistor, and because this is short, and we have this another 20 ohm resistor, then we can make the equivalent resistance of two 20 ohm resistors which are in parallel, which gives us 10 ohm. So it will be parallel RLC circuit, but the resistance is now 10 ohm. So now alpha is, we determine alpha 1 over 2 RC, which is 6.5, omega naught, we substitute L and C, 2.5. Then if we see alpha is greater than omega naught, so alpha greater than omega naught means overdamped solution, which is we have I of t is Is, the steady state value, plus the transient, which is A1 e raised to minus alpha t plus A2 A2 e raised the two roots, S1 and S2, A1 e raised to minus S1t plus A2 e raised to minus S2t. Okay, where S1 and S2 are the two roots by solving this equation. And I at 0 now is 4 ampere. So by substituting t equal to 0, we have 4 equal to 4 plus A1 plus A2. Then from this A2 is equal to minus A1. And now from the second initial condition is L di by dt at 0, which is equal to V at 0. What is V at 0? V at 0, as we found it, V at 0, the capacitor voltage at 0 is 15 volt. So this is 15 volt, but we take the derivative of this. The derivative of the first part is 0. The derivative of the second part is minus 11.978 times A1 e to the power of 11.978, and the derivative of the second part. And then we have this. Then we evaluate at t equal to 0, because A2 is equal to minus A1, and I have this another equation, two equations with two unknowns. We can solve for A1 and A2. And finally, we get I of t given by this. Now, what is IR of t? The current through the resistor. It is the voltage divided by the voltage across is divided by 20, and the voltage across the 20 ohm resistor is the same as the voltage across the capacitor. So we take the voltage across the capacitor. Then we have V of t is L di by dt, okay, which is the same as the voltage also across the inductor. And finally, we find this. Okay, this is a practice problem, and you should be able to solve this. This is also a parallel RLC circuit, step response for parallel RLC circuit. Therefore, to summarize, if we want to solve either series RLC circuit or parallel RLC circuit, first we need to determine, we need to find the initial conditions. We need to x at 0, and this x can be the current or the voltage, and the derivative of x at 0, which is the voltage or current. We determine alpha and omega naught, and then from that, by using alpha and omega naught, we find the form of the response, which can be overdamped, critically damped, or underdamped. And we solve for the constants using the initial conditions, x at 0 and the derivative of x at 0. And if and then to find the complete solution will be the steady state value plus the transient value. for the steady state value, we take the limit as t goes to infinity, okay? And we keep in mind the capacitor will become an open circuit and the inductor is a short circuit at steady state. Okay, now what if we have a general second order circuit? Okay, to solve a general second order circuit, which can be series, parallel, or a combination of series and parallel, we need to follow similar steps. Okay, so the complete solution will be the transient x at t will be the transient response plus the steady state response. Remember, the transient response is without the source, and the steady state response is the response at when as t goes to infinity. Okay. Of course, we take the initial conditions x at 0 and the derivative of x at 0 to solve for the constants. To find the transient response, what we do, we turn off all voltage sources, all independent sources. Okay, for example, if it's a voltage source, we short circuit, and if it's a current source, we open circuit, and we solve for the transient response. And finally, we, using the initial conditions, we solve the constants, and we get the complete solution. Let's have, for example, this general second order circuit. And this circuit at t equals to 0, the switch is closed at t equal to 0. That means before t equals to 0, this was open and the inductor reached the steady state and the capacitor reached the steady state. That means the inductor is short circuit, the capacitor is open circuit. So what is required is find the voltage V, across the capacitor and the current I for t greater than 0. So for t less than 0, the inductor is short and the capacitor is open. In that case, what is the voltage across the capacitor? Simply the 12 volt, because if the capacitor is open, the voltage at 0 minus will be 12 volt. Okay? No current flows through the capacitor, so the source voltage 12 volt will be the capacitor voltage. What about the current I at 0 minus? It is 0. Why? Because again the inductor is short and the capacitor is open, and open circuit, and of course this was open before. Now we found V at 0 and I at 0, 0. And what is C dV by dt? C dV by dt is IC, and dV by dt is IC over C. So the derivative of the voltage at t equals 0 is IC at t equal to 0 divided by C. And by using KCL, I at 0 after the switch is closed, I at 0 plus is equal to IC at 0 plus V at 0 plus divided by 2. V at 0 plus is the voltage across the capacitor, 12 divided by 2. I at 0 plus, the current through the inductor is 0. Therefore, IC at 0 plus is minus 6 ampere. From this, we get the derivative of the voltage at 0, which is minus 12. So we get the two initial conditions, V at 0, 12 volt, and the derivative of V at 0 minus 12. Then what is I at infinity, the final value of the inductor voltage? The final value of the inductor voltage after the switch is closed. After the switch is closed, this is short. Then that means the circuit reaches steady state, and again this will be open. So it will be 12 divided by 4 plus 2. 12 divided by 4 plus 2 ampere. What about V at infinity? The voltage across the capacitor at infinity. It is simply the voltage across the 2 ohm resistor. That is 2 times I at infinity, which is equal to 4 volt. So we found V at infinity, I at infinity. Okay, now by using KCL, I current through the inductor is the voltage, the current through the 2 ohm resistor V over 2 plus the current through the capacitor C dV by dt. Okay, and applying KVL to the left mesh, that means this mesh. Okay, so in this mesh we have 12 volt equals 4I plus L di by dt plus the 2I, okay, times I. So 4I plus L di by dt plus the voltage V is equal to Vs. Then we substitute I, this one. After we substitute, we get this equation, and finally after simplification we have this. If you see this is a second order differential equation, and what is the parameter? The parameter is V, and we can be able to solve this by making Vs is equal to 0. We get the transient response, okay, and V at infinity, the steady state value of the voltage is equal to, okay, the voltage across the capacitor is 12 times, by voltage division, 12 times 2 over 2 plus 4, which is equal to 4 volt. So we need to solve this one, the transient response. Okay, we determine alpha and omega naught. This is 5 is alpha over 2. So alpha is 5 over 2. Omega naught is the square root of 6, which is equal to 2.45. Then alpha is greater than omega naught. So what kind of solution is this? This is overdamped. So I have A e raised to S1t plus B e raised to S2t. And we have the steady state value, which is 4. And by having the initial condition V at 0 and the derivative of V at 0, we solve for A and B. And finally, we get V of t given by this. And after we get the voltage V, the current I, we get it from this equation. Okay, so we solved both the voltage V for t greater than 0 and I for t greater than 0. Okay, so to summarize, so how we solve again general second order circuit. We determine the initial condition x at 0, the derivative of x at 0, and we will find the form of the transient response. Okay, by that, how do we find the transient response? By removing all independent, by turning off all independent source, the voltage source short circuit, the current source open circuit, and we find the form of the transient response, which can be overdamped, critically damped, or underdamped. And using the initial conditions, we solve for the constants. That's all. In these two lectures, we studied a second order circuit. In the first part, we studied source-free series RLC circuit and source-free parallel RLC circuit. In this lecture, step response of series RLC circuit and parallel RLC circuit. Please revise the examples in the slides, and also please practice with problems in the slides. And if you have questions, you can always email me. And thank you for listening to this lecture.